Hello everybody and welcome to day 16 of Advent of Code 2022. Today we'll be finding our way through Volcano and there are gonna be elephants for some reason. So in this problem we are stuck in a volcano full of magma and pressurized gas, and we need to get elephants which are stuck there for some reason out of there and quickly. We have only 30 minutes before the volcano erupts and we don't have time to take each elephant separately, so we need to find a way to make it as efficient as possible. But there is luckily a network of pipes and pressure release valves that we can use to achieve this. So let's see what happens. So there's each valve has a flow rate which tells you how much gas it can release per minute if opened. We are standing in the room that's labeled AA. And it takes 1 minute to open a single valve and 1 minute to follow any tunnel from one valve to another. And our key, the thing that we're trying to figure out is how much pressure we can release. Well, this is the input. I will take it right now and put it into my file here. And all of the valves begin closed. We start at AA and that one does not do anything useful. So there is flow rate of 0. But we can move to BP, which has flow rate of 13. The taking there is gonna take us 1 minute. And 1 minute to open, so we will have 28 minutes or multiplied by 13 to for it to actually be useful, so 364. And then we can move to another valve and open it, which gives us more flow and so on. And here's some probably like the optimal solution. So this releases 1651. So let's first implement the reading of the input. That's going to be the simplest part of this. And I will maybe use regex again here. So in this case, the input is this. And I will do a regex that will give us valve. All right, Z, A to Z. That's gonna be the first group, the valve name equals, then a number, so it's gonna be 0 to 9 multiple times and a semicolon. So this is the second group. And then we need the list of valves. So valves, and the last thing will be this. Okay, so there can be valves or valve. So we need this. And right, so this can be, this is what we need, I think. All right, so this is the regex that we need for this one. So this one, now we will have our lines. And now for each line. And I will store this in some useful format, like a class valve, of course. So it's gonna be have a property of name, property of tunnels, and bottleneck and pressure. Right, and I will create a constructor so it's easier to use. So string names and pressure and valve tunnels. Oh, let's store it as string array and just assign these. Tunnels. And remove the setters so they are read-only, just for simplicity sake. And what else? So we'll read these and store them in some dictionary. So valves, dictionary of string valve. So this way we'll be able to quickly navigate between them by using the string of the name string, and we'll get the valve this way quite easily. Maybe the name property is not even necessary, but let's keep it. Doesn't matter. So we'll, yes, this seems pretty nice. So matches, we'll get matches on that line, and now we will parse the values. So all right, that's fine. We have just one match. Groups one. Group one will be the name, then the value, the connections. Seems this Copilot has already seen this problem before, so the connections are there technically and is separated by comma and space, so that's fine. And this should give us all we need. So let's see if this works. So I will do just a console write line here so I can see what the valves contain. So the valves now contain 10 valves, AA, BB, so it's AA value, A0 pressure, DD, II, BB, DD, II, BB. Let's see some which are, so DD maybe, this one should have some pressure in it, so it's DD20 and the tunnel CCAA EE. Yes, okay, so that's all good. Tunnels, there is just one tunnel. Yes, okay. So we have now the input red. And now for the solution itself, because we need to find a way to go through that tunnel in an efficient way. So to find the best possible solution, which has the most flow rate, we need to find a path that gives us the most flow. And it cannot be a shortest path algorithm, because in that case we would need to find a minimum, and in this case we need to find a maximum. We need to step through the vertices of the graph to find the biggest total sum in a least amount of steps, and each step costs us. So each step costs us one 1 minute, and opening a valve costs us also 1 minute. So it might also be that we will step through 2 tunnels and then open a valve, because it wasn't efficient to, no, it wasn't useful to open the previous one because it was too small. It would cost us 1 minute extra. So it's gonna be some kind of recursive algorithm, but it's gonna be interesting to find, to see how to keep track of our requirements. So find solution. Let's just start drafting it. So we'll have our position here, which is the position where we are currently, and we will have some kind of total. Total pressure and best pressure. So that will be the best one that we so far have found. So it's going to be total pressure, and when we're on a position, there are always 2 options what we can do. We can either stay on it and not move. We can, well, not moving, not doing anything is never useful, so that's not an option. We can open the valve, or we can move. So that is that. We also right. We also need to keep track of which valves are already open. Or maybe not open, but which have been visited, because we don't want to. Yeah, we might want to return to a valve. So we need to keep track which are open currently. So in this simple example, there are just 10 valves. In the full example, full input, there is much more of them, clearly. So there is 60 different valves. Right, we can just have a Boolean array of this open valves. Well, technically, if we have already visited a valve and we haven't opened it, there is no reason to reopen it. To open it after we return, because we have handled that case before. That, like, it's not useful to open a valve later. Can it be useful? Yes, it might be useful to open a valve later when we return to it, because we might have first gone to open another one which has much higher capacity, and then returned to this one to open it to add some additional value. So yes, we need to keep track of open valves, because we cannot reopen them accidentally. Find solution. AA. Total pressure 0. Open valves. Okay, let's pool and valve. So in the beginning, none of them is open. So now for each step, okay, and we need to also keep track of the time where we are there. So this way. So the time is 0. And now, so current valve's position. So now we have two options: open, move. So if the current valve pressure equals to 0, there is no reason to open it. If it's higher than 0, then it's worth opening it. So we can open it. So we will spend 1 minute opening it. So we'll find solution 4. Current valve. We're on the same position. So we're on the same position. Total pressure is current valve pressure times time. Time left. Let's use time left instead. So times time left. So if we have at the beginning 30 minutes, we move 1. I can do this. So time left. So, and we need to open the valve. So open valves. Right, we need to index them somehow, and I will probably just use a dictionary. ID. I just have an ID for them. Just for simplicity's sake. So, and counter plus. So each will have a 0-based ID, and I will just use this as the indexer. So ID true. So if the valve is not already open, then we open it. After we do it, then we reclose it. So that's the opening part. Now, for the moving part, we will do through each tunnel, and we'll find the solution. After going there, it costs us 1 step. The total pressure doesn't change. The open valves don't change. Okay, and if we reach the time limit, time left equals 0, we need to stop trying. So if the time left is 0, then we try to see if we found a better solution than before. This is very simple, but it's probably not gonna finish because it's a lot of recursion going on, and that's costly. It doesn't even reach this point. Right. So this is for the simple sample. It's already taking quite a big amount of time. $16.51. Yeah, okay. We have improved it. Let's see. When we reach this, well, just to see if we can find the best solution, or if the calculation itself is correct. Just that, just to confirm that at least. Okay. What's our current best? 15, 14. Not much. It's still far off from the best solution. It's taking way too long for it to be the correct solution. So we'll need to optimize more. What can we do to optimize it? So if we're at a point in time where if you're on a location 1632. That's almost there. But we need something more efficient here. Need to cut down on the possibilities somehow. But how do we cut down on them? We need to skip many of those which are not prospective enough, but how do we do that? Well, in total, we can open at most 15 valves. That is one move open, one move open, one move open. So 15 valves can be open. At most 15 can be open. So there is so 15 valves can be opened. That's cutting down on the number of cases, but position, sonic position, we go somewhere. How can we efficiently simplify this? Open it, and close it. If it's already open, it will go through this here. Right. So if we return back, so what matters if we return back or not? Do we open it later? If we imagine a scenario where we have one big valve, one small valve in the center, and there is like a star-shaped tunnel system which leads to much better valves. We might be just going to those and back all the time and try opening those 15 or like 14 valves, well, it's probably less, but and not on opening the one that's in the middle, which has just a low value for it to be useful to open it. It could happen. So what do we do? Still not, we don't have the best solution here. Like we could store the situation we are in to avoid returning to the same configuration which we already seen before. So we could have like string for the current position, and current position total, so int total pressure, int time left, and we could encode the open valves using a long 64-bit integer. So long, that's fine. Open valves. Because each inch valve can be yes, this is it. So we can check if it's open or not, and use this to open it and close it afterwards. This way. Wrong. What is that? Long? Yes, it should fix it. Ah, right. Uh-huh. Is that correct? So now we have 0 open at the beginning. Long, encoded, so visited. And yeah, we don't need to store the pressure, we need to store only this. So if we visit it, so dictionary. If we visit a given position at this given time with the same number of open valves, it's worth going there only if we improve our best solution so far. So like this, we could store the best pressures for each configuration. And left. Open valves. So if we already have visited at this point, and yes, is better than the total pressure V, and else we, in other cases, we store it as is. So this will cut down the number of cases a little bit. Because we have 60 valves in the extended example, we could just skip those which are... Okay, it was quick. Best pressure is 0. Okay, that's not great. Right. Let's see why it's always ending. DT 0, 1, 1. All zeros. Cool. It never gets here. Because why? Why? What am I missing? D. What time left? 29. What? Oh, so this check is not working. Not equal to 0. That's the right check. Right. Huh? End it again? Right. So what is wrong here? Ah, right. Again, flip the check. I'm doing this often. So now we'll be opening the valve. That's good. What is this? It's always so quick. Huh. Oh. So this is promising. Let's try with the big input, but this is much bigger. So I am expecting some trouble here. Less pressure. Oh, okay. We have 986. Oh, okay. I'm surprised by this, but we have the first part solved. Cool. All right. So this trick with storing the already visited and no longer interesting solutions has helped us significantly cut down the number of visits, and we're no longer visiting duplicate scenarios, and that works. Okay, so second part of the problem. In this case, we are asking one of the elephants to help us, and instead of having 30 minutes, we have only 26 minutes, because we take 4 minutes to explain to the elephant how to do this. And we try to, again, maximize the pressure, But in this case, the elephant is helping us by so now there are basically two positions to track, and the elephant moves with us. Whew. So this adds one more dimension to this whole problem. So instead of, I will just use the simple input again to debug things. So instead of the elephant going, so instead of having one position, we have our position, and also elephant position, and total pressure and time left and so on. So everything is duplicate now. So our position, elephant position, and now our valve, elephant valve ID. We'll have one more ID entry in the dictionary. There's gonna be a lot of data there. I'm not sure what's gonna happen. So in each case, elephant valve ID. Okay, so this is gonna be a brain teaser, because in each case, either we or elephant or both of us can open a valve, and then we move either we always move both, but there's just our tunnel, our valve tunnels. But we just both of us moving, so it's gonna be like this. That's gonna be a lot of recursion. Good thing to notice here is that it doesn't matter if we are in on a valve or elephant is on a valve. It's like the same thing. So we should probably sort those two values. So it doesn't matter who will arrive there, and if we switch positions, it's basically the same situation, just swapped. So instead of this, we'll cut half of the situations this way. Okay, but still quite a way to go. open. So. Sure. Valve, our valve, our valve. Position, elephant position. Is it ever worth for the elephant not to open the valve if we are opening it? Yes, it might be useful because the elephant can move while we are opening the valve. I see. Right, so now this no longer works this way. Right. Well, the simple case is be both open valve. So let's do like this. We can open. Elephant can open. Yeah. And if we are on the same spot, then elephant cannot open. Because only one of us can open, so we always assume that we are the ones that are opening. So we can open, and not elephant can open. So we open. The valve. Well, if both of us can open, we open both. And only we open. So this will be. We can open, an elephant can open. And this will be only elephant can open. And I think it means that when we open a valve, it's never useful for the elephant to just stand idle, and instead it should move somewhere. So for each elephant tunnel, we will move the elephant there. Our position. So we do this. Does that make sense? So we stand on the same position, elephant moves, we increase pressure and time moves, and open valves change. So the same thing happens when only the elephant opens. where elephant valve is the right one. Our tunnel, our valve. So our position changes to a tunnel, and elephant position doesn't change. The pressure changes. To elephant valve pressure times time left, and elephant valve is changing by, so we open that and close it afterwards. And then we have to handle the case where we both open at the same time and don't move. So, as elephant valve. Just to make it symmetrical, elephant valve. And now we stand on the same position. The pressure has changed by this plus elephant valve pressure times time left. And yes, this is a messy solution, but why not? It could work, even though it's very complex. Let's see what happens. Best pressure is now 980. $17.7. Oh, what is wrong there? Something's wrong there. We got too big of a solution. So why is it wrong? Let's see. It's most likely some kind of mix-up in these our valve, elephant valve, elephant valve. Right, this is wrong. Not we can open and elephant can open. Oh, oh. Right, so. This is the correct one, but we have still too high value there. We had 26 minutes, that's important. I'm working with the wrong input here. 707. Okay. Ooh. That seems very intriguing. Let's see what happens against the full input. is running. Yeah, against the big input, it's gonna be taking longer. Significantly. The question is, how much longer? What's our current best? 841. That's not much. Huh. Right. This could take long. So how do we optimize this? Well, one optimization would be to move this up, because the most likely scenario will be that we both open at the same time, because therein lies the efficiency, that we're parallelizing the work. So maybe this will give us some advantage in the run time. 744. Okay. But still not as efficient as it could be, probably. So how can we improve it further? So we know that we can strip down those cases where we have the same positions just swapped. That thing we are taking care of here. No way to improve that, I'm afraid. So what else? How can we improve this more? Is it ever useful for us not to open anything? It probably is, because in the first position we need to move both. Yeah, it seems to be that in some cases it's just more efficient to move both at the same time. The current best pressure. 1200 is 43. It's not a huge number. Well, like, we could wait for it, but I would rather find a more efficient solution if possible. But I will not stop it, of course. It would be a waste, because maybe it will finish. Our tunnel, elephant tunnel. Total pressure, open valves, yes. So this is the moving part. We both move. Can we simplify this? If we're on the same tunnel, it's not worth trying the other to move like to the same position, only swapped. So we could cut down on the for each, but that's just calling less times the method, which immediately terminates because of the dictionary here. So this will not help us too much. We need to get the best pressure. We need to do this. This is definitely important. So So one improvement that comes to mind is that we could, for each location, we could also remember the best pressure we can achieve from that configuration onwards. So that when we find a better way to that configuration, we can just sum it up with what the configuration has given us before. So that could be done. Okay. I'll just push this for now, so I don't break this working solution, and I will run it in the background so that it's running, and we can maybe it can solve itself. Why not? So run without debugging, and let's try to do this. So when we are, we'll update this to return best solution. Pressure. It's fine. We use this. We can use this best pressure here, but when we are here, we will return total pressure, which will give us the number of what we can achieve on the way there. When we already been there with a better solution, we will just return best, because it doesn't matter, we don't care about not improving. I'm not sure why I'm using long here. It can be int. That's fine. It cannot be bigger than 1000 or something. So what is this? What am I doing wrong? Yeah, it's int. Oh, this is long. Okay. This one is long and this one is int. And now we will have to remember best for current configuration is gonna be 0. And we will remember what is the best we can achieve. So find solution. So basically we just update all of those find solution calls with this. Because this way, after we are done with all those calls, we know what's the best we can achieve. And then we know what was the best cost from that point over, from that point onward. So best from here is best for current configuration minus total pressure. So what we can store best onwards, and store the best from a given point. So best onwards for this configuration. And we can store it. So when we next time hit the same configuration, what we can do is take the best and yeah, if we can store the best. If there is if there is the best onwards, we can skip the rest. So best onwards best path from here onwards. Very wordy. Then we can return then we know that the total pressure that we can achieve is total pressure plus equals best path from here onwards. So we can zero the time and so we can set the time to 1 so that we then zero it out afterwards, and yeah, okay, like this, and we have the best pressure. So not all code returns a value which is true, but why? Because it doesn't return here. So in here, as for current configuration. That could be it. Let's see. So this isn't finished, so I will just kill it. I will just verify if this modified version works for the simple scenario, because that's quite important, so that we know that we didn't break it. And it's quite possible that we broke it. Oh, is it 901 is too much? That's too much. That is too much. Why is it too much? Okay, what did I do wrong? Let's see. This thing cannot work somehow. best pressures from configuration, just for clarity. Okay, so we need to return this here. Mm-hmm. Okay, why is it not there? If we didn't improve it. If we didn't improve it, then if we already have been here with a better configuration, then there is no reason to check further. Can it be 0 here? Maybe it can just return 0. Hmm. 707, okay. But not sure what was wrong there. Not completely sure. But let's try to run it against the big file. It's still running, so it's still taking its time. But we're far faster than before. We're already on 1500. So there was an improvement. 1780. Okay. It's going much faster now. So that's an improvement. Yeah, just returning was incorrect because I was returning the best path for other configuration that I got there with. Yes, so yeah, it's yes, okay, that makes sense. So that was not correct. So if now 272, wow, that's a lot of pressure. 2000, it cannot be too much bigger than the previous solution, but it should be bigger. 2000, 1986 was the previous solution, so it can be at most double that. But we're coming closer to the final value probably. It should be close. And if you wouldn't run with debugger, it might have been much faster even, so. Still improving. What do we have here? Alright, we're very close to the double value from before, and much better. It cannot be much better, so it should soon stop trying. Okay, this is starting to be a little bit dangerous. Shouldn't be much bigger than this. Right, come on. 6 minutes. Huh? Oh, still nothing. Come on, guys. You should be finished by now. 185. Okay, 4013, 4035. Okay, there's a lot of improvements there. We're still improving. That's odd. I think that this is too big now. Too big of a number. I just tried to see if what it will tell me. Too high, right? So they were trying to guess something which is too high. So where can we go overboard with this? If we already encountered a better pressure on this same configuration, there's no use improving it, and we just kill this whole thing and return 0. Because that's not a solution. Not a better solution for the same configuration. If we found a better one, then we store it. Decrease the time left. And there we have the bug, because we're decreasing the time left and trying to get the configuration for a different right. No, it's actually is that right? Because if we, let's see, let's take the sample input from here. Put it here, run it. Okay, Stack Overflow. So if we have this, 707, so it could be this. It could be this. Okay, 76. Okay, 2,880. So before we had the time left decreased here, which meant we were searching for the time left value from that point onwards. Which actually doesn't seem wrong when I think about it now. Yeah, this is too high already. So we're still missing something. But what? This is way too high. Okay. So Right. Yeah, the time left should be the one decreased by 1. So that is fine. The total pressure doesn't change from the beginning here. Except for this one case where we short circuit the calculation because we already went through this configuration to the others. So we found the best pressure from that configuration onwards. So we know that how much it will cost to get forward with the same time, with the same positions. So we can just short circuit this and get here. So this, when we set the time to 0, we always get here. So we always try to improve the best pressure. And then return the total pressure, which is now accurately reflecting the best one. Well, technically, now that we have this best pressure here, we shouldn't need to have it as a separate variable. It should be returned if the implementation is correct. So now solution. So now best pressure is gone. And we need to remove it from the inner part. If time left 0, return total pressure. So if the calculation is correctly implemented, then we should get the same value from here. 707. That seems to be working, but it does not work for our XID. So this one didn't change, this one didn't change, this one decreased by 1, but that's fine. This one didn't. This one is coming from one of those 4 cases. And this one yeah. Okay, let's see. I'll put in the whole input, run it. just to see what's happening when we hit this line. Alright, I will let it run for a while. Then we see when it starts to go ugly, because there must be a situation where it starts to return too high of values. It's gonna be hard to see from this point of view. So now we even don't get any minus 95. Whoa, that is curious. Right. And that's because of the return here for this one. This is an odd one. It short circuits the calculation for this position. It's returning the best solution there. So it should be this way. Probably should be this way. But again, let's try it on the simple input so that we know that we don't break it. 19.1. Why is it 19.1? Because of what? We no longer we got to this configuration in some with the same open valves, with the same time left, with the same min ID and max ID, but it's not the best one. We got there with better pressure. So we took a different path to get there. So why does it seem to improve our result, even though it shouldn't? Why does it improve the path if there is the same? It's the same configuration, it's the same time, it's the same, exactly the same thing. Bigger than? That's just guessing now. It's still wrong, but we go to the same configuration with different value. That means that we were able to open develops in a more efficient way than what we have now. So by returning to that previous point in time, this is not we cannot so we return this pressure because we cannot fake it. We cannot fake that we were more efficient. Right, we can maybe, it's possible that we are overwriting a better configuration. That could happen. If we found a better configuration, or if we improved, then we set it. Here. And we return somehow it's 7, but I don't think that could be the problem there, because if we would just add more steps, but we wouldn't give too high answer. So I will just use this as a temporary thing. So again, we are going to some very, very large values. So what's wrong? What's wrong here? What's wrong? What is wrong? Uh, 3,900. I put a breakpoint here. So I get notified when we go to much higher values than we should have. Okay, so let's do a sanity check again. So at the beginning there are no open valves. We are on the same positions. There is 0 pressure and 26 minutes time left. Time left. Okay, total pressure, elephant valve, our valve. We open, elephant opens. We shouldn't ever get to the point where the value is so big. It's so weird. Somehow we're opening more valves than possible. So now the total pressure is exactly what we have. So best pressure from configuration is 3,432. Okay, let's investigate. So this, we need to see this number as a calculator. We need to see this as a binary number. Okay, no, this way, but that's to pin. Ah, right, of course. That's why it wasn't working. So now, as a binary, you have these ones open, just 4. And from this configuration, we are going to or 1000. So previously we had just like 1000 something. And we will open. Okay, let's do one more thing. Because I still don't understand why on this input, this is now working right. But yes, but if we're returning 0 here, it will not work. Or will it? It does work. But without this adjustment, it will not. It does. So what was it? It was causing that trouble. Huh. Could this be it? Could really this be the problem? That we're closing some valves accidentally because there was no L? It could be it. That could very, very easily be it. Okay, now the value is much lower, and it might actually be it because we didn't use L there, and if we don't use L and we have int here, it was an int, so it could have overflown. It could have overflown. It could very easily be the problem. Because it was behaving like it seemed like we are opening more valves than a human, well, possible in those scenarios. So it could be that we are reopening valves because this was closing or reopening some which were not even relevant in that case, or something like that. Let's see. So far it seems like the value of the best solution value is growing much slower than before, which is a good sign because we were reaching 4000s very quickly before. So 502. Like the fact that it's going slower, it's not a big deal. It's just that there's a lot of cases that need to be evaluated, but it's increasing slowly, so that's a good sign. Let's wait for it. I'll play another song. $17,57. So we're slowly getting to the best value we had before in the first part of the problem. So it was 1900 something, 86. $1,800. Alright, reaching the point of interest, so 1986 should be the one. Okay, still some way to go. Let's see how the memory looks. 17 gigabytes of memory, that's not too shabby. But it's not increasing anymore, it seems like it's staying stable. We are not adding much new configurations to the table. But it's still a lot, so... Oh. 2009, so we already are above the previous best solution. Yes. Still same. I'm thinking if there is a way that we could speed it up still, but This is a good optimization. Like, it should cut down a lot of tries. $2,207. Already a lot. So what can we do to improve this further? I really don't have any more ideas to improve this. It's still going, and I don't see any meaningful improvement there. And yeah, this is growing beyond limits. What could we do? What could we do? We are cutting down configurations that we have seen that have, when we get there in a better way, we stop trying. When we get to the same configuration and we know that what's the best from there, we immediately cut down on that. So what else could we simplify? What else could we simplify? I really don't know. We have best solution now. Okay, let's see if it's correct one or not. Okay, so that's the right answer. But the execution took very long. So I'm really curious to know if there is a way to improve it, or save on memory, or skip something, because this took a long time to execute. So yeah, I will have to probably check some other solutions to see if what others were using, what approach or what shortcut could there be. Maybe there would be a way to cut down on the cases which are obviously not going to work, like when we are in minute 15 and we have no pressure open, or like some kind of heuristic to cut down on the cases which are not useful. Because in those cases, when we wait till the very last minute to open the first valve, that's obviously not gonna work. So we could calculate like the minimum value that we need to have by some point in time, and then all the cases that are trying to get there in that configuration, the skill. It could be it, but I'm not sure how to make this more efficiently. Anyways, we have the solution, so that's a good thing. So I will just force push and add the second part. Yes, so force push. So we have day 16, and I thank you for joining for this very long day, for this very long solution, and hopefully the next one will be easier, but it's good that we have another day solved. So just 2 more to catch up and 1 more when it becomes available on December 19th. But anyways, thank you for joining. See you next time and keep coding, and bye bye.